Astronomers detect a mysterious blast of radio waves. They believe this is one of the most distant and energetic signals ever observed.
Anything that gets close to it becomes its weapon.
Something strange is happening on Jupiter's moon Io.
Nothing's really certain about what's going to happen.
No spacecraft has ever flown this close to
NASA's Juno probe, which has been orbiting Jupiter since 2016.
We are learning that Juno has found an FM signal emanating from one of the gas giant's moons.
Which has been orbiting Jupiter since 2016, has picked up radio signals that seem to be coming from Io itself. While it might sound like the plot of a sci-fi movie, these signals are a natural phenomenon, but an incredibly fascinating one. Could Io, the most volcanic body in the solar system, be communicating with us in ways we're only beginning to understand? Let's dive into what NASA has discovered.
Here's a photograph of the surface of Io. And you see all those colors, all those beautiful yellows.
Before we dive into what makes Io's radio signals so intriguing, it's crucial to understand the spacecraft that made this discovery possible, NASA's Juno probe.
A spacecraft, we're sending a robot there, but really it's our eyes and our ears.
Without Juno's cutting-edge instruments and its daring journey through Jupiter's intense radiation belts, we might have never detected Io's mysterious emissions at all. Launched in 2011, Juno was designed to study Jupiter like never before. Unlike previous missions that kept a safe distance, Juno orbits closer to the gas giant than any spacecraft before it, braving extreme radiation and powerful magnetic fields to gather data. It officially arrived at Jupiter in 2016, entering a highly elliptical orbit that allows it to swing close to the planet before retreating to a safer distance. This path lets Juno capture high-resolution images and measurements without being destroyed by Jupiter's harsh environment. The mission's primary goal is to understand Jupiter's structure, atmosphere, and magnetic field. Scientists want to know what lies beneath its thick cloud cover, how its powerful storms form, and whether it has a solid core. Juno has already transformed our understanding of the gas giant, revealing that its atmosphere is far more complex than expected, with deep swirling jet streams and chaotic storms that stretch thousands of kilometers below the surface. But Juno's mission goes beyond just Jupiter. It also provides invaluable insights into the planet's largest moons, including Ganymede, Europa, and of course Io. These flybys allow Juno to study their surfaces, atmospheres, and interactions with Jupiter's immense magnetosphere. The recent detection of radio waves from Io is just one of many unexpected discoveries the spacecraft has made. Juno's instruments, particularly its Waves radio receiver, play a key role in picking up and analyzing signals from Jupiter and its moons. While radio emissions from Jupiter itself are well documented, scientists were surprised when Juno intercepted a powerful burst of radio waves originating from Io. This wasn't random noise, it was something specific, something connected to the moon's intense volcanic activity. So, what exactly is Io saying through these signals? And how does its unique volcanic nature contribute to this phenomenon? To understand that, we need to take a closer look at this strange and violent moon.
The method that we'll use to probe the interior of Jupiter, and it's all about finding out the recipe for how the solar system was put together.
The most violent world in the solar system. Io is not just another icy rock orbiting Jupiter. Io is the most volcanically active body in the entire solar system, a place where the ground never stops shaking and lava flows stretch for hundreds of kilometers. Io's surface is a chaotic landscape of massive volcanoes, towering lava fountains and sulfuric plains that constantly change due to relentless volcanic activity. Unlike Earth, where volcanic eruptions happen occasionally, Io is in a permanent state of eruption. In fact, some of its volcanoes eject plumes of gas and molten rock that reach hundreds of kilometers into space, so high that they can be seen from Earth with telescopes. This extreme activity is fueled by Io's bizarre position in the Jovian system. Locked in a gravitational tug-of-war between Jupiter and its neighboring moons, Europa and Ganymede, Io is constantly being stretched and squeezed. This process, called tidal heating, generates an immense amount of internal heat, melting rock beneath the surface and creating a never-ending cycle of eruptions. It's this same process that powers the moon's dramatic geological changes, where entire regions can be reshaped in a matter of months. But Io's volcanic nature isn't just about reshaping its surface, It has a much larger effect on the entire Jupiter system. The gases and particles released by its volcanoes get swept up by Jupiter's powerful magnetic field, creating massive plasma waves and electrical currents that link Io directly to the planet. These interactions are so intense that they create a constant stream of energy between the two worlds, forming what scientists call the Io-Jupiter flux tube. This is where things get really interesting. As Io spews out charged particles, they become trapped in Jupiter's magnetic field and generate powerful radio emissions. These signals aren't random noise. They follow a distinct pattern, one that Juno has now detected. But how exactly does this work? And what do these signals tell us about the connection between Io and Jupiter? That's where things start to get even more fascinating.
Detected a highly unusual radio signal. Now the signal, which are apparently coming from
Io's mysterious radio signals are not just noise. Io's volcanic fury doesn't just reshape its own surface, it sends shockwaves through space. As its eruptions release massive amounts of charged particles, Jupiter's intense magnetic field takes over, accelerating them and creating powerful radio emissions. These aren't weak, static-filled whispers. They are structured, high-energy signals that can be detected even from Earth. But what exactly are these signals, and why is NASA's Juno probe picking them up so clearly? The phenomenon behind these emissions is known as decometric radio waves, or DAM emissions. They form when charged particles from Io's volcanic plumes get caught in Jupiter's powerful magnetic field, creating a massive electric circuit between the Moon and the planet. As these charged particles spiral along magnetic field lines, they generate intense radio waves, essentially bursts of electromagnetic energy that Juno's instruments can detect. These signals are not just random bursts of static, they follow specific patterns and frequencies, which scientists have been studying for decades. The emissions are so distinct that, depending on Io's position in its orbit, scientists can predict when these signals will be strongest. When Io moves through certain regions of Jupiter's magnetic field, the interaction intensifies, producing the most powerful emissions. But why is this important? Well, these radio waves carry valuable information about both Io and Jupiter's magnetic environment. By analyzing the signals, scientists can learn more about the plasma interactions around Jupiter, the strength of its magnetic field, and even how energy is transferred between the two bodies. In a way, Io's emissions are like a natural radio beacon, continuously broadcasting data about its extreme environment. What makes Juno's recent detection significant is the level of detail it provides. Previous missions like Voyager and Galileo had already observed these emissions, but Juno's close proximity to Jupiter allows it to capture them with much greater precision. The WAVES instrument on Juno is specifically designed to detect and analyze radio signals in space.
On the Juno mission, we initially launch from the Earth, we fly out.
And its observations are helping scientists refine their understanding of how these emissions work. Interestingly, Io isn't the only celestial body producing these kinds of signals. Other moons, like Ganymede, also create electromagnetic interactions with Jupiter, and even Earth's own auroras generate similar radio waves. However, Io's emissions are by far the strongest and most structured, making them one of the most fascinating natural radio sources in the solar system. So, what does this mean for our understanding of Jupiter and its complex system of moons? And how does Juno's ability to listen in on these signals help us uncover new secrets about the gas giant? That's where things get even more exciting.
Juno, on its approach, managed to capture a movie of Jupiter and its moon.
Juno. Just heard something unbelievable from Io. Juno's ability to detect Io's radio waves isn't just a scientific bonus, it's a game changer. While astronomers have observed these emissions from Earth for decades, Juno's close-range detections provide a level of precision never seen before. But how exactly did the spacecraft hear these signals, and what makes this detection so important? The key to this discovery lies in Juno's WAVES instrument, which was specifically designed to study plasma interactions and radio emissions in Jupiter's magnetosphere. Unlike traditional cameras or spectrometers, WAVES picks up electromagnetic signals in space, allowing scientists to listen to the way charged particles move through Jupiter's intense magnetic field. This makes it ideal for studying Io's decametric radio waves, which are produced when charged particles from Io's volcanic plumes interact with Jupiter's magnetosphere. During one of its recent flybys, Juno passed through a region of intense electromagnetic activity linked directly to Io. As it moved through this zone, waves recorded a series of structured radio emissions, clear, powerful, and unmistakably coming from the Moon's interactions with Jupiter's field. The frequency and strength of these signals confirmed what scientists had suspected. Io's volcanic eruptions are not just shaping its own surface, but actively contributing to Jupiter's immense plasma environment. But Juno's detection wasn't just about confirming an old theory. It provided fresh insights into how these emissions actually behave. By tracking these signals in real time, Juno allowed scientists to map the precise location and movement of Io-generated plasma streams, something that had only been estimated before. It also showed that these emissions are even more dynamic than previously thought, fluctuating based on Io's position in its orbit and changes in its volcanic activity. One of the most fascinating revelations was just how much energy is involved. Io's volcanic material isn't just passively entering Jupiter's magnetosphere, it's actively fueling vast electrical currents that stretch across millions of kilometers of space. These currents connect Io and Jupiter in a way that no other moon-planet system in the solar system does. In fact, if you could somehow see radio waves, this connection would look like a giant invisible lightning bolt continuously striking between the two worlds. For scientists, this detection opens up entirely new ways to study Jupiter's magnetosphere. The more Juno listens to these emissions, the better we understand not just Io's impact on Jupiter, but also how similar processes might work on exoplanets with strong magnetic fields. Could other moons in the universe be producing similar signals? If so, could studying radio waves help us detect volcanic activity on distant worlds? Io's radio messages are telling us more than we ever expected, and Juno is only beginning to decode them. But to fully understand why these emissions exist in the first place, we need to take an even closer look at what drives them, the intense volcanic activity that never stops reshaping Io's surface. Io's volcanic chaos is unlike anything else. Juno's detection of Io's radio waves points to one undeniable fact: Io's volcanic activity is not just extreme, it's powerful enough to influence an entire planetary system. But to truly grasp why Io is so unique, we need to dig deeper into what fuels this non-stop geological chaos. Why is Io, out of all the moons in the solar system, the most volcanically active? At first glance, Io's surface looks nothing like the frozen landscapes of Europa or Ganymede. Instead of icy plains, it's covered in vast lava flows, towering mountains, and enormous pits left behind by past eruptions. The entire moon is painted in shades of yellow, red, and black, thanks to sulfur and molten rock constantly reshaping its surface. Some regions of Io can change dramatically in just a few months, with new lava lakes forming and old ones draining away, creating a constantly shifting landscape unlike anything else in the solar system. The source of all this chaos is tidal heating, a process driven by Io's relationship with Jupiter and its neighboring moons. Unlike Earth's volcanoes, which are powered by internal heat left over from the planet's formation and radioactive decay, Io's volcanic activity is entirely fueled by the immense gravitational forces acting upon it. As Io orbits Jupiter, it is constantly being pulled and stretched by the planet's gravity, but it's not just Jupiter. Europa and Ganymede also exert gravitational forces on Io, creating a complex tug-of-war that literally kneads the moon like dough. This friction generates immense heat deep within Io, melting rock into magma and forcing it toward the surface. The result? A never-ending eruption cycle. Io doesn't just have a few active volcanoes, it has hundreds. Some of the most famous, like Loki Patera, erupt with lava flows that stretch for hundreds of kilometers. Plumes from certain volcanoes have been seen reaching up to 500 kilometers, 310 miles, into space, taller than the distance from Earth's surface to the International Space Station. These eruptions don't just affect Io's surface, they launch massive amounts of sulfur dioxide gas into space, which gets swept up into Jupiter's magnetosphere and contributes to the radio signals Juno detected. Another strange feature of Io's volcanoes is their unpredictability. Unlike on Earth, where eruptions are mostly linked to tectonic plate movement, Io's eruptions are controlled by tidal forces that fluctuate based on its position in orbit. This makes predicting eruptions much more complicated, but also extremely valuable for planetary scientists who want to understand how geological activity works on other worlds. Juno has been flying dangerously close to Io. Studying Io from afar is one thing, but getting up close to this chaotic world is something entirely different. Juno, however, has done just that, flying closer to Io than any spacecraft in over 2 decades. These daring encounters have not only given us some of the most detailed images of Io ever captured, but they've also allowed scientists to directly measure the volcanic activity and electromagnetic chaos that make this moon so unique. Unlike previous missions that briefly passed by Io on their way elsewhere, Juno has been in a long-term orbit around Jupiter, giving it the rare opportunity to observe Io multiple times. In late 2023 and early 2024, Juno executed some of its closest flybys yet, coming within just a few thousand kilometers of Io's surface, a distance that might seem large, but in space terms, it's practically skimming the moon. These close passes have allowed Juno to capture breathtakingly sharp images of Io's surface, revealing fresh lava flows, towering volcanic plumes, and newly formed geological features. Unlike older images from past missions, Juno's photos show changes in near real time, helping scientists understand how quickly Io's landscape is shifting. Some of these changes happen in a matter of weeks, proving just how active the moon really is. But visuals are only part of the story. Juno's instruments have also been recording heat signatures from Io's volcanoes, measuring just how much energy they release. These measurements confirm that some of Io's eruptions are among the most powerful in the solar system, dwarfing even the largest volcanic explosions on Earth. Scientists are particularly interested in Loki Patera, Io's largest volcanic feature, which experiences regular eruptions that could help us predict patterns in tidal heating-driven volcanism. Juno's close encounters have also provided valuable new data on Io's atmosphere, which is largely composed of sulfur dioxide from its eruptions. By analyzing how the thin atmosphere reacts to sunlight and Jupiter's magnetosphere, researchers can better understand how Io interacts with its surroundings. These insights are critical because Io isn't just an isolated world. It plays a key role in shaping Jupiter's entire space environment. However, these close flybys come with risks. Io is surrounded by intense radiation thanks to Jupiter's powerful magnetic field. Every time Juno approaches the moon, it is bombarded with high-energy particles that could potentially damage its instruments. Despite this, the spacecraft has continued its mission, pushing deeper into Io's hazardous environment to gather as much data as possible. Could Io be the next big target for space missions? Juno's close encounters with Io have proven just how much we still have to learn about this volatile world. With every flyby, new details emerge, reshaping our understanding of tidal heating, volcanic activity, and the powerful interactions between moons and planetary magnetospheres. But these discoveries also raise an even bigger question: what comes next? For decades, Io has been somewhat overlooked in planetary exploration. Missions like Galileo and Voyager captured glimpses of its volcanic fury, but their primary focus was elsewhere, on Jupiter itself or the icy moons that might harbor life. Io, despite being an extreme and fascinating world, has remained out of reach for dedicated exploration. That, however, may be about to change. NASA has already begun planning for future missions that could explore Io in much greater detail. One of the most anticipated projects is the Io Volcano Observer, IVO, a proposed mission designed to orbit Jupiter and perform repeated close flybys of Io. Unlike Juno, which was not specifically built for Io exploration, IVO would be optimized to study the moon's extreme volcanic activity, atmospheric changes, and its role in shaping Jupiter's magnetosphere. If approved, it could launch within the next decade. Beyond flybys, scientists are also considering the possibility of landing on Io, a feat that would be incredibly challenging but groundbreaking. A lander could provide direct surface measurements, revealing the true composition of Io's crust, the temperatures of its lava flows, and perhaps even seismic activity beneath its surface. However, such a mission would require advanced heat-resistant technology to survive Io's extreme conditions, as well as shielding to protect against Jupiter's intense radiation. But what do you think? Let us know in the comments below.